You know the air you're breathing right now? Well, it's not calm at all. It's actually in this constant, high-speed frenzy. And today, we're going to uncover the hidden rules of that invisible world. A world that, believe it or not, explains so much of our own. I mean, have you ever stopped to really think about it? Why does a hot air balloon rise up like that? Or what's actually going on inside a tire on a scorching hot day right before it might burst? It turns out these things aren't random at all. They're following a very, very specific set of rules. And the answer, well, it's not in what we can see. It's in the unseen. It's this frantic, invisible dance of trillions of tiny particles, all zipping around at unbelievable speeds. And that is what we call the kinetic theory of gases. All right, first things first, let's zoom way in and take a look at what the air all around us is actually made of. And this is where things get kind of mind-blowing. The air filling this room, it's not some solid, continuous thing. No way. It's actually almost entirely empty space, just populated by billions and billions of individual particles all whizzing around. So these little molecules, they have some pretty unique properties. For one, they're incredibly far apart from each other. I mean, the distance between them is just huge compared to their actual size. They're also in constant, totally random motion, just bouncing off each other and everything else in their path. And that right there is why a gas will always expand to fill any container you put it in. They just don't have a fixed shape or volume. Okay, here's a perfect real-world example you've definitely experienced. You spray some perfume in one corner of a room, right? And a little while later, you can smell it all the way across the room. That's not magic. It's literally just the perfume molecules randomly bouncing and colliding their way through the air until they've spread out everywhere. Okay, so we've got all these particles zipping around randomly. But what happens when they actually hit something? Well, that's what brings us to our next big idea, how all this microscopic motion creates forces that we can actually feel in our world. You know, whenever you feel the air inside a balloon pushing against your hand, what you're really feeling is the combined force of trillions upon trillions of molecules slamming into the inside of that balloon every single second. That's what gas pressure is. It's just the grand total of all those tiny, tiny collisions. So how do you pump up that pressure? It's actually super simple. Just think about pumping up a bike tire. With every single pump, you're just cramming more and more air molecules into the exact same space. More molecules means more collisions with the inside of the tire, and boom, the pressure goes up. All right, let's connect this whole idea to temperature. See, we usually think of temperature as just hot or cold, but in physics, it's way more specific than that. Temperature is nothing more than a measure of how fast, on average, those gas molecules are moving. It's a direct measurement of their kinetic energy, their energy of motion. And the difference is pretty dramatic. In a hot gas, the molecules are just zipping around like crazy. They've got a ton of kinetic energy. But in a cold gas, they're much more sluggish, kind of slow-moving. And hey, this also perfectly explains why hot air rises, right? The faster-moving molecules push each other further apart. That makes the air less dense, and up it floats. Okay, this is the part where it all clicks into place. We've seen how these tiny molecules move and how they create pressure. So now, let's connect all that microscopic action to the famous big picture laws that govern gases. Because here's the amazing thing. What looks like total chaos down at the molecular level, all those random bounces and collisions, it all averages out to create these beautiful, predictable patterns that we can see and measure. So the famous gas laws, they're not some kind of magic formula. Nope, they are a direct result of all that molecular motion. Let's just take two of the big ones. You've got Boyle's law, which says if you shrink a container, the pressure goes up. And now we know why, right? You're just crowding the molecules together, so they're going to hit the walls way more often. Then there's Charles's law. Heat a gas, and it expands. Again, makes perfect sense. You make the molecules move faster, so they hit the walls harder and more frequently, pushing those walls outward. See? It all just works. But, you know, like any great scientific theory, this one isn't perfect. It has its limits. The whole thing is based on a simplified model of what we call a perfect or an ideal gas. So let's talk about where that perfect model starts to break down when it meets messy, complicated reality. So to make all the math work out nicely, scientists basically came up with this idea of an ideal gas. And it has a few key assumptions. First, they pretend the molecules are just tiny points with zero size. They also assume that the molecules don't attract or repel each other at all. And finally, when they collide, it's a perfect bounce. No energy is lost. Think of it like perfect billiard balls hitting, not two lumps of clay sticking together. And honestly, for most gases under normal conditions, like, yeah, the air in this room, these assumptions work brilliantly. They get us super close to predicting what really happens. But we have to remember they are simplifications. And when you push things to the extreme, reality starts to push back. So here's the real takeaway. The ideal gas model works best when molecules are really far apart and moving super fast, so at high temperatures and low pressures. But what happens if you crank the pressure way up or drop the temperature way down? Well, the molecules get squeezed together, and all of a sudden their actual size starts to matter. Those little attractive forces between them, the ones we ignored, they start to take over. And just like that, our perfect ideal model, it doesn't hold up anymore. When you step back and look at it, the kinetic theory of gases is just a masterpiece of scientific modeling. It takes this ridiculously complex reality with trillions of moving parts and gives us a simple, incredibly powerful framework that explains almost everything we see. It is the perfect example of how science uses simplification to achieve understanding. And that really just leaves us with one final thought. We just used a simple model to peek behind the curtain and understand the invisible world that makes the balloon float. It kind of makes you wonder, doesn't it? What other huge, complex systems are out there, all around us, just hidden in plain sight, waiting for the right, simple model to suddenly make them crystal clear?